We look out at the night sky as if it were a map, a place with directions, distances, and meanings we can eventually solve. Yet the first truth is the one we resist the most. The universe contains everything we can touch or imagine, and still, we do not know what it truly is. We measure its galaxies, we trace its light, we model its birth. But when we ask the simplest question, what is the shape of all of this? The cosmos grows strangely silent, because shape is a human comfort. Edges, boundaries, outlines. These are the tools of small minds trying to understand an immeasurable whole. Some say the universe is flat. Others say it curves like a sphere. Some imagine a torus, looping space back into itself, while others whisper that the universe might be infinite, or shaped in ways the human brain cannot yet form into words. And each possibility expands us a little, only to leave us smaller than before. But this is where the journey begins, in the quiet tension between what we believe we know and what the universe has never confirmed. To understand the universe, we must first admit we do not yet know its shape. In the beginning, long before equations carved their symbols into the fabric of understanding, the universe existed only as a story whispered around fires. Humans lifted their eyes to the sky and saw a ceiling, a dome, a protective shell separating the known from the unknowable. It was comforting to imagine an edge, a place where the world ended and the divine began. Because edges made reality manageable, they gave shape to fear and borders to wonder. And in those early nights, when shadows moved like spirits and stars felt close enough to touch, the cosmos seemed small enough to understand, yet mysterious enough to worship. Every ancient culture built its own version of the universe, and each one reflected the shape of the mind that dreamed it. Some imagined a flat world resting on the backs of cosmic animals. Some pictured a layered cosmos, each tier home to gods, winds, or ancestors. Others described the heavens as a crystalline sphere, perfect and eternal, turning with the grace of celestial machinery. These visions were not primitive. They were poetic answers to a question no one had the tools to ask properly. And in their simplicity, they revealed something profound. Humans fear infinity. A universe without borders feels like a threat to the mind that evolved inside tight horizons. So our ancestors placed an edge on everything. They drew the world as a disk circled by oceans that led nowhere. They imagined a roof above it, decorated with lights that never changed position. They placed themselves at the center, not out of arrogance, but out of necessity. A world with an edge is easier to inhabit. It has rules. It has symmetry. It has a place where the unknown stops. And for thousands of years, this illusion protected us. But illusions eventually crack. Sailors ventured farther than the myths allowed. New stars appeared and faded. Shadows shifted with seasons in ways that no flat world could explain. Slowly, painfully, the edges began to dissolve. And yet, humans held on to them. Because the collapse of a boundary is the collapse of a worldview. The cosmos was widening, and we were not ready. When the Greeks stepped into the conversation, their ideas carried both beauty and constraint. Aristotle imagined a universe wrapped in perfect spheres, each one carrying the planets like jewels embedded in crystal. His cosmos was finite, ordered, hierarchical, a structure worthy of gods who preferred geometry over chaos. The earth sat calmly at the center, unmoving, untouched by the imperfections of the outer heavens. Above us lay the realm of perfection. Beyond that, nothing at all. the ultimate edge. For centuries, Aristotle's universe dominated human thought, not because it was correct, but because it was comforting. It preserved the boundary, it protected the mind from infinity. It gave humans a stable place in the cosmic story. And even as observations grew sharper, the desire for an edge held firm. Because if the universe had no edges, then where were we? What did it mean to exist in a place with no center, no boundary, no favored position? These questions arrived too early, and humanity wasn't ready to hold them. Even the great myths mirrored this tension. In many ancient stories, the universe begins as a small enclosed space, a cosmic egg, a primordial cave, a womb of creation. Boundaries birthed existence. Order emerged by defining what lay inside from what lay outside. But what if there was no outside? What if the universe didn't need walls to exist? Such ideas hovered at the edges of ancient thought like forbidden constellations, visible but never fully named. As civilizations advanced, models of the universe became more elaborate, but the instinct remained the same: draw a line somewhere. Ptolemy refined Aristotle's spheres into a clockwork of epicycles. Babylonian astronomers recorded the heavens with astonishing precision, but their maps still implied a finite sky. Even cultures with remarkably accurate star charts clung to the idea that everything fit neatly into a cosmic container. Boundaries were not just scientific guesses, they were psychological anchors. Because the truth is uncomfortable, a universe without edges means we are suspended in something immeasurable. It means the mind must stretch beyond its evolutionary origins, beyond caves, beyond horizons, beyond the instinctive belief that everything must have an end. The ancient world could not yet make that leap, so it wrapped the infinite in shells of imagination. And for a time, that was enough. When philosophers began to challenge these models, the shift was subtle but revolutionary. Some thinkers dared to ask whether the heavens might extend farther than the eye could see. Others wondered whether the stars might be distant suns scattered across immense space. These were not just scientific provocations. They were assaults on the human fear of boundlessness. Because if the universe stretched beyond the last visible star, then where did it stop? How large was too large? At what point does size itself lose meaning? Slowly, the ancient illusion of edges weakened. New tools, new methods, new courage began to peel back the layers. The earth lost its place at the center. The heavens lost their perfection. The firmament cracked open and spilled stars deeper than imagination. Every century pushed the edge farther away. Every discovery made the world bigger and the human mind smaller. And yet, something remarkable happened. Wonder grew. Curiosity expanded. The loss of boundaries did not shrink humanity. It revealed that we were capable of more than smallness. But even today, the ancient instinct survives. We still look for edges. We still ask if the universe has a shape we can point to, define, or draw. We still want the comfort of boundaries. It shows in our language. We speak of the edge of the observable universe, the edge of space-time, the boundary of cosmic inflation. These phrases soothe us, but they hide a deeper truth. The edge we see is not the universe's edge. It is the limit of our perception, a horizon, not a wall. And so, when we compare ancient cosmologies to the modern universe, we find both distance and similarity. Their worlds were small because their tools were small, but their desire for edges, that is timeless. Our ancestors lived in a bounded cosmos because they needed one. And in quiet ways, we still do. Infinity is not just a concept, it is a challenge, a mirror held up to the mind, asking it to grow. Yet growth always begins with a break, a fracture in certainty, a question too large for the story that came before it. And somewhere between those ancient fires and the telescopes of today, a realization began to bloom. Maybe the universe never needed edges. Maybe edges were only the scaffolding we built to steady ourselves while we learned to look outward. The ancient illusions are not mistakes. They are stepping stones. They show us how far the mind has traveled and how far it still must go. Because even now, as science stretches toward truths larger than imagination, we cling to the hope that the universe fits into something familiar. But familiarity is not the nature of the cosmos. Mystery is. Boundlessness is. And so the question that haunted our ancestors returns to us, sharper and wider than ever. If the universe does not end where we once thought it did, does it end at all? If shape itself dissolves at cosmic scales, what are we really living inside? A sphere? A plane? A loop? A structure beyond geometry? Or something so vast that the human notion of edges becomes irrelevant? These questions echo across the centuries, linking those early thinkers to us. Their worlds were small. Ours is enormous. But the feeling is the same. A mix of fear and wonder, confusion and awe. The illusion of edges is fading, but the mind still reaches for something to hold. Yet perhaps letting go is the beginning of understanding, because the universe does not shrink to fit the imagination. The imagination must expand to meet the universe. And once we release our need for boundaries, a deeper possibility emerges, one that feels unsettling, liberating, and infinitely wide. But what if the universe had no edges at all? Before the universe stretched into anything recognizable, before distance meant separation and time meant change, there was a moment so brief and so violent that even calling it a moment feels dishonest. The Planck era, the first seconds of reality, was not a place, not a shape, not a space. It was a storm of raw existence, a seething ocean of quantum foam where space-time flickered in and out of being like sparks dissolving before they could illuminate anything. Nothing held still long enough to be measured. Nothing persisted long enough to be named. The universe was a vibration, a trembling, a probability field with no outline. Even the question where had no meaning, because where requires geometry, and geometry had not yet been born. In that primordial chaos, everything we now call real was suspended in uncertainty. Distances were undefined. Directions were meaningless. The very fabric that would one day cradle galaxies did not yet know how to stretch or fold. Space-time itself behaved like a restless sea, bubbling with microscopic fluctuations, each one rewriting reality faster than the speed of thought. To stand in such a place, if standing were possible, would be to witness existence without form, truth without structure. But that wasn't the end. It was only the prelude. For in this storm of formlessness, potential gathered. Not purpose, not destiny, but possibility, compressed to an unimaginable density. The universe was smaller than an atom, yet contained everything it would ever become. It was neither quiet nor loud, neither light nor dark. It simply was, teetering on the edge between being and non-being. And from this unstable cradle, a transformation ignited, sudden, unstoppable, terrifying in its simplicity. The universe began to inflate, not expand gently, but erupt outward, driven by an energy field so exotic that its nature still eludes us. Inflation did not care about the rules, it wrote them. In less than a heartbeat, space-time stretched faster than light, ballooning from subatomic insignificance to cosmic immensity. Distances expanded so rapidly that regions once touching were ripped apart forever, separated beyond the reach of any signal, any particle, any possibility of reunion. What had been chaotic became smooth. What had been curved became flat. What had been turbulent became eerily uniform. Like a sheet pulled tight over a wild landscape, inflation ironed the universe into simplicity. But simplicity can be deceptive. To us, the cosmos now appears calm, almost elegant, a vast, nearly flat expanse where light behaves predictably and geometry obeys familiar rules. Yet beneath that order lies the violence of its birth. The inflationary surge froze the quantum foam into patterns, stretching microscopic fluctuations to cosmic scales. These frozen ripples became the seeds of galaxies, clusters, voids, the large-scale structure of everything we see today. From formless trembling emerged the scaffolding of the stars. Still, inflation did more than sculpt structure. It concealed truth. Because as the universe expanded faster than any information could travel, it created a horizon, a boundary not of the universe itself, but of our ability to witness it. Everything beyond that horizon is forever inaccessible, not hidden by darkness or distance, but by the rules of space-time itself. We can never know what lies beyond it, never retrieve information from regions that expanded away from us before light could cross the gap. Inflation built a wall not around the cosmos, but within our perception. And so the universe we observe is only a fragment, a sliver of a far larger reality, sculpted by forces we barely understand. Our telescopes reach back billions of years, but they cannot see past the horizon inflation imposed. They cannot reveal the shape that might lie beyond the observable edge. Is the universe curved on scales too large to detect? Does it loop back on itself like a cosmic torus? Does it stretch infinitely, repeating patterns forever? Or does it harbor regions so different from our own that they obey laws we cannot imagine? Inflation does not answer these questions. It deepens them, because it suggests that what we see, this calm, flat, structured cosmos, is not the universe as a whole. It is merely the aftermath of a process that may have sculpted countless other regions, each one expanding beyond its own horizon, each one sealed off from every other by the speed of spacetime's birth. In this view, our universe is not the universe, but one bubble among many, a single note in a cosmic symphony, too vast to hear in full. But even if we set aside the multiverse, one truth remains. The universe's early moments erased its original shape. Whatever geometry the cosmos might have had before inflation is forever lost, stretched beyond recognition. The contours of that primordial state lie so far beyond our horizon that no light, no signal, no particle can ever bring them to us. The inflationary expansion placed them beyond eternity's reach. What we observe now is not the universe's native form. It is the smoothed and simplified version inflation left behind. This realization forces a profound question. If the universe only gained recognizable shape after inflation, then what came before cannot be described by any shape at all. Geometry is a consequence of stability, and stability was profoundly absent during the Planck era. The cosmos did not merely lack edges, it lacked form itself. And perhaps this is the deepest shock. The universe was not born as a place. It became one. Order emerged slowly, shyly. Forces separated. Particles condensed. Light found room to move. The cosmos cooled enough for structure to persist. Space learned how to stretch without tearing. Time learned how to flow without glitching. Only then did the universe begin to look like something we could measure, describe, or imagine. Yet even this emerging order carried the fingerprints of its violent beginning. Slight variations in temperature, minute asymmetries, faint whispers of the quantum storm that preceded shape. The cosmic microwave background is one such whisper, a relic of light from an era when the universe was a storm settling into stillness. And still, one can sense the tension between what inflation reveals and what it hides. We understand enough to know that form was not always possible. But we also understand that we may never recover the universe's lost history. The history before shape, before scale, before time flowed with direction. We are left with clues, with traces, with patterns stretched across the sky like ancient scars. But scars do not tell the whole story. They only hint at the wound. Inflation gave the universe size, but it also stole its origins. It flattened curvature so thoroughly that even if the universe is curved on scales billions of times larger than we can observe, we will never detect it. It accelerated regions away from us so permanently that no future technology can reveal their contents. It shaped a horizon we cannot cross, no matter how far or how long we travel. We live inside a cosmic bubble whose outer walls are not physical but perceptual, and the true shape of the universe, whatever it was, whatever it is, may lie forever outside our reach. Yet this limitation is not a failure. It is an invitation, because the universe that inflation sculpted still carries enough mystery to fill every generation with wonder. And the realization that we cannot see its full shape does not diminish its grandeur. It expands it. It suggests that reality is larger than comprehension, deeper than geometry, stranger than imagination. We look at the universe today and see structure, galaxies arranged like cosmic lace, filaments stretching across unimaginable distances, voids deeper than the darkest silence. But beneath that order lies the memory of an era when shape was impossible, when the universe existed as pure potential waiting to unfold. And the horizon inflation carved still surrounds us, a reminder that our cosmic story began with both revelation and concealment. Inflation sculpted a universe we can observe, but maybe not the universe that truly exists. When we speak of the universe, we often imagine a vast sphere stretching outward in all directions, a bubble of galaxies, stars, and cosmic dust suspended in the darkness. It feels enormous, almost infinite, a boundary so distant that the mind struggles to hold it. But what we call the observable universe is not a map of everything that exists. It is a map of everything that has had time to reach us, a horizon built not from matter, but from light's long journey across expanding space. And that difference changes everything. Look outward far enough and you step into a paradox. The farthest galaxies we see are 46.5 billion light years away, yet the universe itself is only 13.8 billion years old. Light has not traveled that far. Space has stretched that far while light was crossing it. Distance has grown faster than information could keep up. The boundary we see is not a wall. It is a limit created by time, expansion, and the speed of causality. The observable universe is shaped not by where things are, but by what light has been allowed to reveal. And beyond that glowing veil lies a reality our senses cannot touch. To understand this, we must think in terms stranger than geometry. Picture a cone made of light, a backward-reaching funnel that traces every point in space-time from which a photon could have reached your eyes at this exact moment. Everything inside that cone belongs to your observable universe. Everything outside lies forever beyond it, not because it is absent, but because no signal could move fast enough to bridge the widening gap. This light cone grows as time passes, reaching deeper and deeper into cosmic history, pulling new regions into visibility. But even as it grows, the universe expands faster, the horizon keeps moving, and the unreachable stays unreachable. This is why the observable universe is not a sphere carved into space-time. It is the intersection of possibility and time, the overlap between what exists and what can be known. When we draw it as a round bubble, we simplify a truth far more profound. We are surrounded by regions we will never see, never touch, never measure. Not because they are too far, but because space itself is stretching everything apart faster than light can stitch it together. Clarity shrinks as distance grows. Beyond the edge of visibility, reality continues in silence. And this silence carries a subtle danger, the illusion of completeness. Because our instruments point outward and return images, because our maps show galaxies swirling at every angle, we believe we are witnessing the universe itself. But what we are truly witnessing is a cosmic echo, a filtered memory of a younger universe, distorted by expansion and slowed by relativity. The farther we look, the further back in time we travel, until the galaxies we see are not distant in space, but ancient in age. The observable universe is a time machine, and time hides more than it reveals. Consider this. The galaxies at the far edge of visibility are not sitting where we see them. By the time their light reaches us, they have moved billions of light years farther away. Some have already crossed the threshold where no new light will ever reach us again. They have slipped beyond our cosmic event horizon. Not a boundary of matter, but a boundary of future knowledge. Even if we live for trillions of years, nothing from those regions will ever touch us again. They are swallowed by expansion, erased not from existence, but from our reach. This boundary is as real as any coastline, yet it exists without physical structure. And the shape of the observable universe is not a shape the cosmos possesses. It is the shape of our limitations, a light-traced bubble wrapped around our ignorance, a sphere not of matter but of understanding. This realization is unsettling. We are used to thinking of horizons as distant frontiers we can cross with enough courage or technology. But the cosmic horizon is different. It is not a challenge, it is a law. The universe is expanding at every point, in every direction. Not like an explosion, but like rising dough. There is no center because every point is a center. No edge because expansion unfolds everywhere. From our perspective, it feels like we occupy a privileged vantage, a cosmic middle from which everything radiates. But this is an illusion created by relativity. Any observer in any galaxy would see themselves at the center of a sphere of visible stars. The shape of the observable universe is a viewpoint, not a structure. Each observer carries a private bubble of reality tailored by their position in space-time. This leads to a startling truth. The universe we see is not the universe. It is simply the part that has introduced itself, a local patch of a far greater whole, trimmed by light's finite speed and shaped by expansion's relentless push. Beyond our horizon might exist regions with different arrangements of galaxies, different densities, even different physics. Or perhaps the universe repeats, patterned like a cosmic mosaic extending forever. Or perhaps it curves back on itself, looping endlessly in ways our eyes cannot detect. We do not know, and the horizon will not tell us. Even stranger is the way expansion distorts perception. Light traveling toward us is stretched, its wavelength elongated by the movement of space. Distant galaxies glow redder, fainter, older. Eventually, the redshift becomes so extreme that even the light that reaches us is stretched into invisibility. When this happens, galaxies fade, not because they died, but because their signals have been diluted beyond recognition. They become ghosts, present, but unreachable. Their existence persists, but their story becomes unreadable. And soon, even this visible universe will shrink in meaning. Over unimaginable time, expansion will accelerate until most galaxies slide beyond the horizon. The sky will empty. The cosmic web will dim. Future observers, living in a far, far colder universe, will look outward and see almost nothing. Their observable universe will be a lonely island isolated by the expansion that once revealed the cosmos to us. They will never suspect the true scale of what lies beyond. For them, the universe will appear small. For us, it appears grand. But for the cosmos itself, both views are merely illusions of perspective. This raises a deeper question, one that sits quietly beneath every measurement we make. What is the universe really shaped like if every observer only sees their own bubble? If the boundary of visibility is not a physical edge, then our cosmic sphere is not a map, but a mirage, a temporary footprint of what light has had permission to show. And if the true universe extends far beyond this bubble, perhaps infinitely, then the concept of shape itself becomes slippery. Are we living inside something finite but unbounded, infinite but structured, curved on scales so large we cannot detect them, or flat only because inflation stretched away the curvature we might have seen? The observable universe cannot answer these questions. It can only limit them. It gives us clues, whispers, shadows of a much greater truth. It is a mask, not a portrait. And the horizon around us, that glowing edge at 46.5 billion light years, is not the universe's boundary. It is our own. Light reveals, expansion hides, and between them, we stand, holding a map that shows everything we can know today and nothing we cannot know ever. Yet this is not a defeat. It is a doorway. Because the universe we see is extraordinary, not for what it contains, but for what it implies. The very existence of a horizon tells us there is more beyond it. The silence from those unreachable depths is not emptiness. It is invitation, a reminder that our vision is small and reality is wide. So when we speak of the observable universe, we must speak with humility. It is only a bubble of knowledge floating in a sea we cannot chart, a temporary sphere carved by time and expansion, changing with every heartbeat of cosmic history. And the greater universe, whatever its shape, whatever its size, continues far beyond the comforting limits of our cosmic map. And so a question rises, soft but insistent. If the visible universe is not the real universe, what is the real shape? Before we can speak of the universe's true shape, we must confront a quiet truth. Space is not the passive emptiness we imagine. It bends, it curves, it stretches, and folds under the weight of matter and energy, shaping the path of every beam of light and every drifting star. Geometry is not an abstract idea, it is the architecture of reality. And if we can understand how space curves, we can begin to guess the shape of the cosmos itself. But this is not a simple guessing game. It is a journey into the limits of measurement, into a realm where intuition fails and only the faintest clues remain. Einstein revealed something radical. Space and time are not rigid. They respond to energy. Add mass and space curves inward, add expansion and space curves outward. Remove both, and space might be perfectly straight. These possibilities aren't philosophical. They define three great families of universal geometry: flat, spherical, saddle-shaped. Three cosmic blueprints that could determine whether the universe is infinite, finite, or something stranger. But the truth is buried in the details, and the details whisper contradictions. Start with the simplest: a flat universe. In Euclidean space, parallel lines never meet. Triangles add to 180 degrees. Light travels in straight paths unless bent by local gravity. If the universe is flat, it might stretch outward forever, infinite in every direction, a canvas without borders. Or it might be unimaginably large but still finite, wrapped in ways that repeat without revealing themselves. Flatness is deceptive. It tells us nothing about size, only about the absence of detectable curvature on scales we can observe. And our observations? They hint at flatness with eerie precision. But before flatness seduced the modern mind, another shape ruled human imagination: the sphere. A closed universe curves inward on itself, like the surface of a cosmic globe. Travel far enough in one direction, and you might loop back to where you began, not because of boundaries, but because of curvature. A finite universe with no edges, simple, poetic, mathematically elegant. In such a universe, parallel lines eventually meet, and the sum of a triangle's angles exceeds 180 degrees. Everything is contained, held in a cosmic embrace. No infinities, no vast emptiness stretching forever, just a finite whole, complete and self-contained. Then there is the third possibility, perhaps the most unsettling: an open universe, curved like a saddle, forever stretching outward, forever expanding, with parallel lines diverging and triangles adding to less than 180 degrees. This hyperbolic geometry creates a cosmos with structure unlike anything our senses can imagine. It is infinite by necessity, foreign in behavior, and endlessly diluting as expansion accelerates. In such a universe, distance grows faster than meaning. Space opens like a wound that never heals. These three geometries form the basic menu of cosmic shapes, but the universe may not choose any of them in their pure form. And that is where the measurements come in. To decipher cosmic curvature, we examine the oldest light in existence, the cosmic microwave background, a relic from when the universe was only 380,000 years old. Its faint ripples contain encoded signatures of geometry. WMAP scanned these patterns with remarkable clarity. Planck sharpened them further, revealing the geometry of the cosmos with the precision of a cosmic ruler. Their verdict was shocking in its simplicity. The universe appears flat, so flat that if there is curvature, it is too subtle for even our finest instruments to detect. But appearances deceive. Flat in cosmology does not mean straight forever. It means the curvature is too small to measure, too gentle to reveal itself. The difference between perfectly flat and almost flat could extend beyond our observable bubble by factors of 1,000 or 1,000,000,000,000. Our cosmic horizon is too small a window to distinguish between an infinite plane and a colossal sphere so large that the segment we inhabit feels straight. A grain of dust cannot detect the curvature of a planet. We may be the dust. And yet, the evidence piles up. Baryon acoustic oscillations, frozen sound waves from the early universe, trace patterns in galaxy clusters that align with flat geometry. The distribution of galaxies reinforces it. The shape of temperature fluctuations in the CMB strengthens it. Even models of dark energy push us toward flatness as the simplest explanation. And in science, the simplest explanation often becomes the most seductive. But simplicity can mislead. Flatness may be an illusion created by inflation's violent stretching of spacetime. Inflation smoothed the universe so forcefully that any primordial curvature, whether spherical or hyperbolic, would appear flat today, just as the Earth appears flat to someone standing on its surface. Our horizon is too small to reveal the curve. Inflation, in its cosmic efficiency, may have polished away every clue. We are left with precision measurements that all point in the same direction. The universe looks flat, but looking is not knowing. Consider this unsettling possibility. The true curvature could exist beyond our horizon, so faint we will never detect it. The universe might be closed, curved like a grand cosmic sphere, destined one day to slow, stop, and collapse into itself. Or it could be open, curved outward, expanding forever into freezing emptiness. Both possibilities fit the mathematics, both fit the cosmic history, both remain invisible to us. We are trapped inside a region too small to expose the truth. And dark energy complicates everything further. As space accelerates its expansion, it stretches curvature even thinner. It smooths the universe. It hides the shape. Dark energy is like a hand pulling a fabric tight until all folds disappear. But the folds were there once, and they may still exist outside the regions we can observe. When Planck announced that the universe was flat to within a margin of error smaller than 1%, scientists understood the weight of that statement, not because it proved flatness, but because it proved how little we can distinguish. We could be living on a universe-sized sphere so vast that its curvature becomes detectable only at scales millions of times larger than the observable cosmos, or a hyperbolic realm that bends outward in ways we cannot measure, because our instruments are confined to one tiny cosmic bubble, or a truly flat universe, infinite and eternal, stretching beyond comprehension. Every interpretation leads to a different cosmic destiny, a different shape, a different story, and yet all of them produce a universe that looks almost exactly like the one we observe. Geometry hides behind a mask of precision, revealing hints but not truth. The universe plays a quiet trick on us. It lets us see enough to ask the question, but not enough to answer it. Still, there is beauty in this uncertainty. Because the universe's shape is not just a scientific detail, it is a cosmic personality. A curved universe embraces, a flat universe stretches, a hyperbolic universe flees toward infinity. The geometry of reality defines its past and predicts its future. And we stand in the middle, holding instruments too small for a question too large. But we keep asking, and that persistence is its own kind of wonder. So we return to the data, the equations, the ancient light We compare our flat maps against the possibilities that lie beyond their edges, and the answer remains a whisper, almost flat, nearly straight, just shy of zero curvature, a perfection that feels suspicious in a universe defined by imperfection. And that suspicion opens a door to endless speculation. What if flatness is simply what we can see, not what truly is? What if the real geometry hides behind horizons we can never cross? What if curvature exists on scales so immense that our entire observable universe is merely one flat tile in a mosaic too vast to imagine? Because flatness does not mean infinite. It only means too large for us to measure. Before we can ask whether the universe is infinite or finite, we must ask a stranger question. What if the universe has no edges because it wraps around itself? Not metaphorically, literally. What if traveling far enough in one direction brings you quietly back to where you started? Not because you hit a wall and turned, but because space itself is curved in a way the human mind is not built to picture? This is the realm of cosmic topology, the study of how space might fold, loop, twist, or connect to itself across dimensions we cannot perceive. And here, the universe stops behaving like a simple container and begins acting like a puzzle, a labyrinth, a shape that is finite, yet endlessly continuous. Topology ignores appearances and asks a deeper question. How is space connected? A piece of paper and a donut look nothing alike, but mathematically they share a hidden similarity. Both are surfaces without boundaries. The universe might follow such hidden rules. Its shape may not be what it looks like, but how it folds beneath our perception. And this is where intuition fails us, because the universe does not need to obey the geometry of human experience. It can loop in ways no eye can see, fold in ways no hand can feel, and repeat in ways no mind can easily imagine. Yet the equations of general relativity and quantum cosmology quietly allow such structures. They do not forbid them. They invite them. Begin with the simplest of the strange, the three torus. Imagine a video game map where leaving the screen on the left makes you reappear on the right. Now extend that idea into three spatial dimensions. In a toroidal universe, if you travel far enough in one direction, you eventually return to your starting point, not by curving downward, but by crossing a seamless transition that connects opposite sides of space. It is finite in volume, but infinite in experience because no path ever ends. Light itself would loop through the universe, creating repeating patterns in the cosmic microwave background. You might one day look into a telescope and, unknowingly, see the back of your own head, billions of years younger. A cosmic mirror, not of reflection, but of topology. But the torus is only the beginning. Imagine a hypersphere, a four-dimensional analogues of a sphere. We cannot visualize it. Our senses evolved on planes and caves, not in hyperspaces. Yet the mathematics is clear. In a hyperspherical universe, every straight path eventually curves back to its origin, finite without edges, closed without boundaries. A universe that contains itself the way a dream loops into its own beginning. Some cosmological models flirt with this idea, suggesting that if the density of matter were just slightly higher, our universe might have curled into such a hyperspherical shape. And even now, if dark energy behaves differently over time, this topology could still be waiting beyond our observational horizon. Then there is something even stranger, the Poincare dodecahedral space, an idea as elegant as it is disorienting. Picture a 12-faced dodecahedron, each face connected to its opposite face with a twist. Travel through one pentagonal face, and you re-enter the universe from another, rotated and reoriented. In such a universe, space is not merely finite, it is artistically finite, symmetrical, repeating with a kind of cosmic choreography. The Poincaré universe would imprint subtle, repeating circles on the cosmic microwave background, fingerprints of its looping structure. Some researchers once thought they saw these signatures in the WMAP data, though later measurements blurred the claim. But the possibility remains, lingering like an unanswered question written into the sky. Topology grows stranger as we move deeper into mathematics. Consider a crystallized universe, a cosmic mosaic, where space repeats itself in regular patterns like tiles on an infinite floor. Each tile is not a place, but a copy of a place, replicated endlessly by the fundamental structure of spacetime. Quantum gravity allows such repetition. Higher dimensional models even encourage it, suggesting that what we perceive as continuous space might actually be a repeating lattice too subtle for our senses, like a pattern hidden in fog. In such universes, there is no far away. There is only again. And then there is the possibility of a multi-connected cosmos, where space folds and tunnels back into itself through higher dimensional shortcuts. Not wormholes exactly, but something quieter. Identifications of distant regions, stitching space-time like a quilt that hides its seams. In such a universe, light does not travel freely. It follows these hidden identifications, creating patterns that appear random until the underlying topology is understood. The universe becomes a hall of echoes, where distant galaxies might be multiple images of the same object seen along different topological paths. These shapes defy vision. They defy analogy. They refuse to be pictured inside a human skull because the human skull evolved to navigate distances measured in footsteps, not in billions of light years. Our intuition insists that space stretches outward like a simple sheet, but topology whispers otherwise. It hints that the universe might be finite in ways that do not resemble any shape we have ever held or imagined. It suggests that edges are illusions, that boundaries are human inventions, and that the cosmos may loop in directions we cannot turn toward. And the deeper we look, the more tantalizing the clues become. The cosmic microwave background, a snapshot of the infant universe, carries subtle patterns, cold spots, alignments, and anomalies that some physicists argue are better explained by a finite, multi-connected topology than by an infinite flat space. Perhaps these patterns are just noise, artifacts of measurement, statistical accidents, or perhaps they are hints of something profound, a shadow of the universe wrapping around itself, a whisper of structure far beyond our horizon, a message not from another universe, but from another part of this one, folded just out of sight. Modern cosmology walks a thin line between what is observed and what is allowed, and topology lives entirely in that gap. The universe looks flat, but flatness does not forbid loops. The universe appears vast, but vastness does not guarantee infinity. Inflation smoothed the cosmos so thoroughly that any repeating structures would be enormously wide, perhaps wider than our visible bubble. If the universe loops, it might do so on scales so immense that no telescope we build today could detect it. The cosmic horizon hides both curvature and connectivity. The very same expansion that reveals the large-scale universe is the expansion that conceals its true shape. But the implications are staggering. If the universe is a torus, then infinity dissolves into repetition. If it is a hypersphere, then the cosmos curls into a seamless whole. If it is a Poincare space, then reality is a grand 12-sided loop. If it is a cosmic crystal, then existence becomes a tessellated pattern with no center and no edge. And if it is multi-connected, then distance ceases to have a single meaning. Near and far become matters of topology, not geometry. We might already be surrounded by multiple versions of the same galaxies, the same structures, the same ancient light, stitched together by dimensions we cannot see. What makes these ideas so profound is not just their strangeness, it is their plausibility. Physics allows them. Mathematics supports them. Observations do not rule them out. The universe could be looping right now silently, invisibly, elegantly, while we draw straight lines through a space that may not be straight at all. And our minds, born from the simplicity of Earth, may never fully grasp what it means to move through a space that connects to itself. Topology reminds us that the universe does not owe us simplicity. It owes us nothing at all. And yet it gives us hints, just enough to ask the question, never enough to answer it. That tension, that yearning for clarity, is what makes cosmic topology one of the most mesmerizing frontiers of science. It is where imagination meets mathematics, where philosophy meets physics, where the familiar dissolves into the impossible. And so we are left with a universe that may be finite without edges, complete without boundaries, looping without end. A universe that might be small in volume but infinite in experience. A universe that could carry us in circles so vast that we mistake them for straight lines. A universe whose true shape hides behind horizons we can never cross, wrapped in dimensions we can never see. What if the universe is finite, but in a way the human mind cannot visualize? Infinity is a word we speak with ease, yet barely understand. It slips off the tongue like something familiar, yet when we follow it to its edges, we find none. It stretches beyond comprehension, beyond logic, beyond the architecture of the human mind. And yet, here we stand, asking whether the universe, the totality of existence, might truly be infinite, not poetically, not symbolically, but in the literal, physical sense. A cosmos with no boundary, no ending, no final frontier. A reality so vast that every direction continues without pause, without closure, without mercy. The question is simple. The implications are not. Because to ask whether the universe is infinite is to step into a paradox older than thought itself. Infinity is not a number. It is not a size. It is a structure, a way of being that defies the very language we use to describe it. In mathematics, infinity is an idea that can be manipulated, partitioned, combined, and compared. There are infinities larger than other infinities. There are infinities so vast they make others feel small. But physics is not mathematics. Reality does not bend to symbols. If the universe is infinite in volume, then it contains an infinite amount of matter, energy, and entropy. Infinite stars, infinite galaxies, infinite distances, infinite versions of you repeating endlessly in configurations so close and so different that the mind collapses under the weight of imagining them. But does physics allow such extravagance? Or is infinity merely a mathematical mirage, a placeholder for we do not know? The first challenge to an infinite universe is physical. An infinite amount of mass energy should curve space infinitely. Yet observations show the universe is astonishingly flat. Not perfectly, just almost. So nearly flat that curvature, if it exists, is spread across scales far beyond the observable horizon. This suggests either a universe so vast it might as well be infinite, or a universe exactly infinite. Both options sit uncomfortably in the mind, demanding an expansion of imagination. Then comes the second paradox. If the universe is infinite, then every possible arrangement of particles occurs somewhere. Every story repeats. Every history unfolds again in some distant region. The fabric of existence becomes a cosmic library of every possible world, most unseen, most unreachable, most forever separated from our own by distances too great to cross. This is not speculation. It is a consequence of infinite space paired with finite physical laws. And that consequence unsettles us because it steals uniqueness from existence. In an infinite universe, nothing is singular. Everything is duplicated, even you. But before we accept or reject infinity, we must venture deeper into the machinery of cosmic creation, to the concept of eternal inflation. In the early universe, inflation did not simply stretch space once and stop. The equation suggests that inflation continues in other regions even now, endlessly, eternally, spawning new bubble universes in a wild fractal cascade. Each bubble is a universe with its own laws, its own constants, its own beginning. Some expand, some collapse, some endure. This infinite flowering of universes forms what physicists call the megaverse, a structure not merely big, but unending, a fractal of realities branching forever. In this picture, our universe is not infinite in size, but the multiverse is infinite in structure. Infinity appears not as extension, but as repetition, not as size, but as process. Inflation becomes the engine of infinity, converting vacuum energy into endless pockets of space-time. And the horizon we see becomes the boundary not of all reality, but of our local bubble, a drop in an ocean with no shores. Yet eternal inflation introduces new complications. If the megaverse is infinite, does that infinity live in space, or in time, or in both? Can anything truly begin in a structure without end? If infinite universes exist, why do we inhabit this one? Are we typical, or are we rare? And what does rare even mean in a place where probability dissolves? These questions turn infinity from a scientific inquiry into a philosophical storm, blurring the line between physics and metaphysics. A deeper challenge emerges from quantum mechanics. At the smallest scales, the vacuum is not empty. It is a sea of fluctuations that appear and vanish incessantly. Under the right conditions, these fluctuations can seed entire universes, budding off from the quantum fabric like sparks from a fire. If quantum fluctuations never cease, and if each fluctuation has a small but non-zero chance of triggering inflation, then universes are not created once. They are created forever. Reality becomes a self-replicating pattern, an endless generator of cosmos after cosmos, each one oblivious to the others except through the shared mathematics that predicted them. In this picture, infinity is not about size. It is about recurrence, a process without conclusion, a story without a final chapter. But what if infinity itself is an illusion, a failure of human cognition? The mind evolved to hunt, to survive, to navigate distances no greater than a horizon. Infinity was never part of its design. When we try to imagine something without end, our thoughts loop, they stall, they collapse into abstraction. The brain cannot picture infinity because the brain itself is finite. And so the idea remains forever out of reach, like trying to grasp a shadow cast by something outside the room. Still, mathematics insists on infinity's legitimacy. The calculus of physics depends on it. The equations of spacetime allow it. But whether physical infinity exists is a different matter. Some theories argue the universe must be finite because infinite energy violates thermodynamic principles. Others argue infinity is the simplest solution, the natural outcome of unbounded expansion. Neither side has won. Neither side is likely to. The horizon swallows all proof. Perhaps the problem is not the universe. Perhaps the problem is language. What we call infinite may simply mean too large to measure. What we call finite may hide complexities beyond detection. A universe that loops on scales 1,000,000,000 times larger than our horizon is technically finite, yet indistinguishable from infinity. And a universe that expands forever may be infinite in time, but not in space. Infinity fractures into categories the mind cannot unify. What if infinity is not a thing to be discovered, but a boundary we create when understanding fails? What if the universe does not end, not because it is infinite, but because end is a human idea, irrelevant to a cosmos that does not need edges to exist? The universe may be finite in volume, yet eternal in creation. It may be infinite in structure, but not in size. Or it may contain infinities folded within its topology, loops that repeat without expanding forever. When we confront infinity, we are not confronting the cosmos. We are confronting ourselves, the smallness of human intuition, the limits of language, the fragility of understanding. And yet, there is beauty in this confrontation, because infinity, whether real or imagined, forces awe. It forces humility. It forces the mind to stretch beyond every comfort it has ever known. So does the universe ever end? The truth may be this: endings are for stories. Boundaries are for maps. Edges are for minds that evolved in finite worlds. The cosmos has no obligation to provide us with closure. Infinity might exist, or it might not. But either way, the mind will always find its limits long before the universe finds its own. Perhaps the universe is not infinite. Perhaps the mind is simply too small. Before we can finish the search for the universe's true shape, we must confront a final and unsettling possibility that the shape we seek is not a shape we can see, not with eyes, not with intuition, not even with imagination. For most of human history, we assumed the universe unfolded in the familiar language of length, width, and height, three dimensions woven into a fabric we could picture like a vast cosmic landscape. But the deeper physics goes, the more that certainty dissolves. Space may not be three-dimensional at all. The universe may curve, fold, and resonate in directions hidden from our senses, dimensions so small or so strange that we move through them without knowing they exist. And if the universe's true shape lives in these unseen dimensions, then everything we've ever pictured, spheres, saddles, toruses, loops, may be nothing more than shadows cast by a higher dimensional truth. String theory was the first great whisper of this revelation. It suggested that the fundamental particles we see, electrons, quarks, photons, are not points, but tiny vibrating strings. Their vibrations determine their properties, just as the vibration of a violin string determines its note. But strings cannot vibrate properly in three dimensions. They require more room, 10 dimensions for the theory to make sense. 6 of these dimensions, the theory says, are curled up so tightly that they evade detection, compactified into spaces called Calabi-Yau manifolds. These manifolds are not shapes in any visual sense. They are mathematical objects, intricate beyond human intuition, and yet they may define everything: the constants of physics, the particles that exist, even the very structure of the cosmos. Imagine this: the universe you see is just the three-dimensional surface of a shape that extends into directions you cannot perceive. Like a shadow on a wall trying to understand the object that casts it. The shadow sees edges, curves, angles, but not the depth behind them. We may be that shadow. The universe we observe may be a projection of something grander, folded into dimensions beyond reach. Brain cosmology takes this idea further. In string theory's higher dimensional framework, entire universes can exist as membranes, brains, floating in a higher dimensional space called the bulk. Our universe might be a three-dimensional brain drifting through this multidimensional ocean. Everything we know, matter, light, forces, may be trapped on this brain, unable to move into the higher dimensions. Only gravity, faint and elusive, can leak across the extra-dimensional divide, revealing the presence of invisible depths, like ripples, passing between parallel surfaces. If this is true, then the universe's shape is not merely a question of geometry. It is a question of embedding. We are not living in space. We are living on a surface of a much larger structure, and the shape of that larger structure may determine the fate of the cosmos itself. Consider the ekpyrotic model, a bold proposal in which the universe didn't begin with a singularity, but with the collision of two brains. In this picture, the Big Bang was not an explosion from nothing, but the spark created when higher dimensional worlds brushed against each other. Space and time unfolded like shock waves from a cosmic impact, and after billions of years, the brains may drift and collide again, birthing universe after universe in an eternal, rhythmic cycle. In such a reality, our universe is not an isolated bubble, but one moment in an infinite sequence of higher dimensional interactions. Its shape, its history, and its boundaries are determined not solely by what happens within it, but by what happens outside it. In the dimensions we cannot see, here, space is not a container. It is a participant, a dynamic entity shaped by motions in realms beyond perception, a ripple in a higher sea. But the hardest challenge comes next. If extra dimensions exist, how do they curve? How do they fold? What shape do they impose on the cosmos? In general relativity, mass and energy tell space-time how to curve, but in higher dimensional theories, the curvature of the extra dimensions can determine the behavior of the three we inhabit. A tiny twist in a hidden dimension could change the mass of a particle. A subtle fold could create the illusion of cosmic flatness. A small vibration could alter the strength of gravity across the universe. The true shape of reality could be governed by geometries that exist at scales far smaller than atoms, yet whose influence stretches across billions of light years. This is perhaps the greatest irony. The universe may look flat, not because it is flat, but because higher dimensional curvature forces it to appear that way. Like a sheet of paper held taut by the shape of the hand that grasps it. We see only the sheet, we do not see the hand. And if the hand moves, the sheet follows. So we begin to confront an unsettling truth. The universe's visible geometry may be a mask. Everything we measure, curvature, expansion, topology, may be an emergent property of hidden dimensions shaping our world from behind the veil. We stand in 3 dimensions like a fish in a lake, unaware of the sky above, unaware that the surface enclosing us is not the true limit of existence. The fish sees only water. We see only space. But what lies beyond? String theory offers 10 dimensions. M theory offers 11. Some quantum gravity researchers propose infinite dimensions emerging from fractal structures. Others suggest dimensions that are not spatial at all. Conceptual dimensions, informational dimensions, mathematical dimensions that shape reality without occupying space. In these models, asking for the universe's shape becomes like asking for the color of time or the taste of gravity. The question dissolves because the thing being described defies the form of the question. And yet, the mathematics persists. It builds universes of breathtaking complexity, worlds where the fabric of space is woven from symmetries invisible to human perception. We cannot picture these dimensions, but equations can. They draw shapes the mind cannot visualize, but whose implications fill the cosmos. Perhaps the universe bends where we cannot follow. Perhaps it loops in dimensions we cannot turn toward. Perhaps what we call space is a projection of higher dimensional truths. Truths that remain hidden, not because they are far away, but because they lie at right angles to existence as we know it. Even our language fails here. We try to speak of folding, twisting, compactifying, but these are metaphors borrowed from a world of objects. The universe may not fold, it may not twist, it may not loop, it may do something for which we have no word, something only mathematics knows how to describe, something that cannot be drawn, cannot be pictured, cannot be imagined, only approached gently through abstraction. And this is where humility reaches its peak. The cosmos is not obligated to fit inside the container of human intuition. Our senses were forged in a 3-dimensional wilderness. They were shaped by survival, not by truth. Higher dimensions may exist, whether we can imagine them or not. They may govern the universe, whether we acknowledge them or not. They may be the real stage on which reality unfolds, while our familiar 3 dimensions are just the surface scenery of a much deeper play. So the question returns quiet and profound. What is the true shape of the universe? A sphere, a saddle, a torus, a loop, a crystal, or something that has no name because it has no analog in the world we know? If the universe hides in higher dimensions, can a 3-dimensional mind ever truly grasp its shape? We return to the question that first opened the door, a question too large for language, too quiet for certainty. What is the true shape of the universe? After all the theories, the maps, the equations, the loops and folds and higher dimensional whispers, the answer does not arrive as clarity, it arrives as humility. Because the universe may be finite or infinite, curved or flat, looping like a cosmic echo or branching into dimensions we cannot follow. It may be a sphere without edges, a plane without end, a mosaic repeating into eternity, or a tapestry woven from structures no human mind has ever conceived. And still, it exists effortlessly without needing our understanding to complete it. We are the ones who crave shape. The universe simply is. The more we learn, the more its boundaries blur. The more we measure, the more its edges dissolve. Each discovery widens the horizon. only to reveal that the horizon was never the limit, only the beginning of a deeper mystery. And perhaps this is the quiet truth hidden beneath every cosmological question. The universe was never meant to fit inside the human mind. The mind must grow, stretch, and transform to even glimpse the vastness it tries to hold. So we let go of the need to solve the cosmos and embrace the act of reaching toward it. We allow wonder to replace certainty. We allow curiosity to outlive answers. We stand in the space between knowing and not knowing, and we find peace there, because the universe is not a puzzle to be completed, but a horizon meant to pull us forward. And so the question circles back to where it began. Softer now, almost like a promise. The universe may be beyond shape, but so is our capacity to wonder.